Assalamu alaikum, dear students. Welcome to the course Principle in Animal Life 1. This is lecture number 41. The topic is enzymes. Discussing agenda for the topic is enzymes, and they speed up metabolic reactions by lowering energy barriers, the activation energy barrier, and how enzymes speed up reactions. Lecture outcome. After watching and listening this lecture, students will know about enzymes and how they catalyze chemical reactions. Introduction. Enzymes speed up metabolic reactions by lowering energy barriers. The laws of thermodynamics tells us what will and will not happen under given conditions, but say nothing about the rate of these reactions, at which pace the reactions will occur. A spontaneous chemical reaction occurs without any requirement for outside energy. So a spontaneous chemical reactions, they are usually occurring without an input of energy. This is in opposition to the endothermic reactions, which requires the input of energy. So endothermic reactions are non-spontaneous, but it may occur so slowly that it is imperceptible. So spontaneous reactions, although they can occur without the input of energy, but they occur at such a slow pace which is not perceived. For example, even though the hydrolysis of sucrose, a table sugar, to glucose and fructose is exergonic, it's exothermic, means the energy is released when the hydrolysis of sucrose occurs. So this process is spontaneous, and the energy which is released is delta G minus 7 kilocalories per mole. Delta G refers to the energy available to perform work. So this exergonic reaction produces this amount of energy which can be used to perform work. Now, a solution of sucrose dissolved in sterile water, clean water, will sit for years at room temperature with no appreciable hydrolysis. So the sugar will not dissolve in sterile water placed at room temperature. But if we add a small amount of the enzyme sucrase to the solution, then all the sucrose may be hydrolyzed within seconds, as shown in that chemical reaction. This is sucrose, the table sugar, and it is present in water. Its hydrolysis is occurring. If this process occurs in the presence of sucrase enzyme, it will be in seconds. So this sucrase enzyme is increasing the speed of this reaction, a reaction which will normally take years to complete can complete within milliseconds in the presence of an enzyme. How do the enzymes do this? How they catalyze the reactions? How the reactions proceed so fast under the effect of the enzymes? What are the enzymes? Enzymes are macromolecules, predominantly proteins, that act as catalysts, a chemical agent that speed up a reaction without being consumed by the reaction. Enzymes are not consumed in a chemical reaction. They are recovered at the end of the reaction and can be used to catalyze other reactions. Without regulation by enzymes, chemical traffic through the pathways of metabolism would become terribly congested. Means there will be lot of problems in undertaking those multi-step metabolic pathways, because there will be buildup of substrates at different points. In the next two sections, we will see why spontaneous reactions can be slow and how an enzyme changes the situation. Now, remember, we have introduced enzymes. Enzymes are predominantly proteins. They are proteins in nature, but this is not a universal fact. There are some exceptional conditions where enzymes are also found which are not proteinaceous in nature. For example, RNA molecules can also act as an enzyme, and such RNA molecules are called ribozymes. Now, the activation energy barrier. Activation energy is the minimum amount of energy required to convert reactants into products. Every chemical reaction between molecules involves both bond breaking and bond forming. For example, the hydrolysis of sucrose involves breaking the bond between glucose and fructose. And one of the bonds of a water molecule and then forming two new bonds as shown in the figure you just saw. You will go back there. So here you can see this is bond breaking process. Similarly, the water molecule is also dissociated, and then the hydrogen and hydroxyl ions, they form bond with the glucose and fructose, the two monomers. So on the left side, bond breaking process is underway, and on the right side there is a formation of a bond where hydroxyl binds with glucose and hydrogen binds with the fructose. So changing one molecule into another generally involves contorting. Now, what is contorting? It is twist or bend out of the normal shape, the starting molecule into a highly unstable state before the reaction can proceed. When the reactants are in stable state or in the ground state, then it is difficult to convert them into products unless they are excited, they are provided with energy which makes them unstable. Only then they will be converted into products. This contortion can be compared to the bending of a metal key ring. When you pry it open, force it open to add a new key. This is a key ring. If you want to introduce a key into this ring, then you will have to pry it open. Obviously, its stable state is this one, but you want a new key to be introduced in here, so therefore you must open it. When you open it, it will come into an unstable form, and the key will be introduced into it, and when you leave it, it will return back to its original position. So here they have compared this analogy with the substrate molecules which are in stable state, but if the product is intended from these substrate molecules, then they must be brought into an unstable form. The key ring is highly unstable in its opened form, but returns to a stable state once the key is threaded all the way into the ring. To reach the contorted state where bonds can change, reactant molecules must absorb energy from their surroundings. Just like when you pry it open, you provide energy, and then when you introduce a key, so it's a kind of a reaction which is completed. Similarly, the reactants are in stable state, and if they does not absorb energy, they will not become excited or destabilized, and therefore they will not convert into products. So this absorption of energy is important to bring the reactants into an unstable form. When the new bonds of the product molecules form, energy is released as heat, and the molecule return to stable shapes with lower energy than the contorted state. The initial investment of energy for starting a reaction, the energy required to contort the reactant molecules so the bonds can break, is known as the free energy of activation or activation energy. So activation energy is the energy required to convert reactants into products or to make reactants unstable so that they can be converted into products. We can think of activation energy as the amount of energy needed to push the reactants to the top of an energy barrier or uphill so that the downhill part of the reaction can begin. Activation energy is often supplied by heat in the form of thermal energy, which makes the bonds unstable. The reactant molecules absorb from the surroundings. So usually in an endothermic reactions, this energy which is supplied is used to destabilize the molecule and to break the bonds. The absorption of thermal energy accelerates the reactant molecules so they collide more often and more forcefully. It also agitates the atoms within the molecule, making the breakage of bonds more likely. Now here, when the molecules have absorbed enough energy for the bonds to break, the reactants are in an unstable condition. known as the transition state. So this is the ground state. In that state, this reaction will not proceed. The reactants must be supplied with some energy so that they come to a transition or an unstable stage, and only then they will form products. So AB plus CD, these are the reactants, and then AC plus B, these are the products, AC plus BD. The activation of the reactants is represented by the uphill portion of the graph, in which the free energy content of the reactant molecules is increasing. So here, if you want those stable molecules to come into an unstable state, then you will have to provide that activation energy. Now, once this activation energy breaks the bonds, then the energy will be released to the surroundings, and once again the products will come to even lower energy state than the reactants. At the summit, when energy equivalent to EA has been absorbed, the reactants are in transition state. They are activated and their bonds can be broken. As the atoms then settle into their new, more stable bonding arrangements, energy is released to the surroundings. This corresponds to the downhill part of the curve, which shows the loss of free energy by the molecules. Once again, you are seeing this word free energy means the energy which is available to perform work. So when these molecules in transition state, they return to the ground state. So obviously it will only happen when the energy they have absorbed is released, and this released energy can be used to perform some kind of work. The overall decrease in free energy means the activation energy is repaid with dividends, as the formation of new bonds release more energy than was invested in the breaking of old bonds. So the activation energy which is provided is yielded again when these molecules returns to when the products returns to the ground state. In most cases, however, activation energy is so high and the transition state is reached so rarely that the reaction will hardly proceed at all. Now, this was a hypothetical example where they showed that the reactant molecules must be brought into a transition state, and only then the conditions will be feasible for the breakage of the bonds and the conversion of the reactants into products. In normal circumstances, inside a living cell, some of the reactions need so much activation energy that it is impossible to provide those reactions with that much of activation energy. The release of that much activation energy suddenly will even result in the death of the cell and more and this reaction will not be feasible for the cell. In these cases, the reaction will occur at a noticeable rate only if energy is provided, usually by heat. For example, the reaction of gasoline and oxygen is exergonic and will occur spontaneously. But energy is required for the molecules to reach the transition state and react. Only when the spark plugs fire in an automobile engine can there be the explosive release of energy that pushes the piston. So although the breakdown of gasoline is itself an exergonic process where energy is released that drives the vehicle, but to begin the process some of the energy input is required. Without a spark, a mixture of gasoline, hydrocarbon and oxygen will not react because the activation barrier is too high. In these cases, the reaction will occur at a noticeable rate only if energy is provided, usually by heat. Repeated slide. Now proteins, DNA and other complex cellular molecules are rich in free energy, means when these molecules are broken down they can release energy which can be used elsewhere and have the potential to decompose spontaneously. This is the laws of thermodynamics favor their breakdown. These molecules only persist because at temperature typical for cells, few molecules can make it over the hump of activation energy. The barrier for selected reactions must occasionally be surmounted. However, for cells to carry out the processes needed for life, now some of the reactions are so much important for the existence and for the survival of the cell and the organism that those reactions must be completed, even though they will require a high input of energy, but still the organism cannot survive without the completion of those reactions. Heat can increase the rate of a reaction by allowing reactants to attain the transition state more often, but this would not work well in biological systems because biological systems cannot afford to accumulate so much heat. First, high temperature denature proteins and kill cells. Second, heat would speed up all reactions, not just those that are needed. So these are the two consequences if the organism provides the heat energy to a reaction which requires a high input of energy, because this provision of heat will have drastic effects on other structures in the cell and overall on the sovereignty of the cell. It will denature proteins and this heat will also speed up other reactions, means it will hamper the regulations of enzyme activities for other reactions. Now here you can see the reactants must be converted into products, and those reactants must be provided with an activation energy so that they can be brought to a transition stage where it is more feasible to break their bonds. Now it is difficult to provide them with that amount of heat energy because it is harmful for the cell. So what will happen? Enzymes will lower down the activation energy. Now activation energy is at that level, and with the introduction of the enzymes this level will decrease, so it will be much easier for the reactants to cross this barrier as compared to this one. The process by which a catalyst selectively speeds up a reaction without itself being consumed. This is the definition of catalysis. An enzyme catalyzes a reaction by lowering the activation energy. So this is a very important sentence, and perhaps it is the summary of the last 2-3 slides. Enabling the reactant molecules to absorb enough energy to reach the transition state even at moderate temperatures, as well as shortly, as we will see shortly. It is crucial to note that an enzyme cannot change the free energy for a reaction. Now, an enzyme cannot change the free energy. An enzyme will have no contribution to the overall energy of the reaction. It cannot make an endergonic reaction exergonic. Enzymes can only hasten reactions that would eventually occur anyway. But this enables the cell to have a dynamic metabolism, routing chemicals smoothly through metabolic pathways. Also, enzymes are very specific for the reactions they catalyze. This is very important for the regulation of the metabolic activities. So they determine which chemical process will be going on in the cell at any given time. This was the end of the lecture. Thank you.